Hey, everybody. Welcome to the podcast. I'm Ben Wilson.
Hey, everyone. It's Michael Berk. How's it going?
And today we're going to have a bit of a panelist discussion that's focused more on internals of ML work and some statistical theory.
Hey folks, this is Charles Max Wood from Top End Devs, and lately I've been working on actually building out Top End Devs. If you're interested, you can go to topenddevs.com/podcast, and you can actually hear a little bit more about my story, about why I'm doing what I'm doing with Top End Devs, why I changed it from devchat.tv to Top End Devs. But what I really want to get into is that I have decided that I'm going to build the platform that I always wished I had with devchat.tv. And I renamed it to Top End Devs because I want to give you the resources that are going to help you to build the career that you want, right? So whether you want to be an influencer in tech, whether you want to go and just max out your salary and then go live a lifestyle with your family, your friends, or just traveling the world or whatever, I want to give you the resources that are going to help you do that. We're going to have career and leadership resources in there, and we're going to be giving you content on a regular basis to help you level up and max out your career. So go check it out at topenddevs.com. If you sign up before my birthday, that's December 14th. If you sign up before my birthday, you can get 50% off the lifetime of your subscription. Once again, that's topenddevs.com.
Before we started recording here today, we were talking about a great post that Michael wrote a while ago called How to Handle Uncertainty in Forecasts. And it covers a part of data science work that I've seen people struggle with a little bit, and its foundations are incredibly important for many ML use cases. So, Michael, if you want to talk about what it is that you wrote about and how important it is.
Yeah, for sure. So you guys asked for nerdy topics, and you shall receive. Today, we're going to be talking about prediction intervals. And prediction intervals are exactly what they sound like. They're confidence intervals around a prediction. So everybody knows what a confidence interval is. Well, we just place that around a prediction, and then we have uncertainty bounds with 95% probability or whatever probability that you select. By the way, sorry if my voice is a little scratchy. I'm feeling a little bit under the weather. But yeah, so that's the general premise for today. A while back, I found a method called conformal prediction or conformal inference. And it was making waves in when it first came out in around 2017, because it was the only universally valid method to provide prediction intervals under a misspecified model. So what that means is no matter how wrong your model is, we should see coverage according to whatever alpha level you select. So 95%, 80%, 66%, whatever it is. So that's the concept in a nutshell.
So when we're talking about confidence intervals around a prediction, a lot of people see an ML model, and let's say we're talking about a binary classifier. We're classifying, in your blog post, you're doing an example of binary classification on an image showing either a cow or a camel. And when people look at the output of a predict function called on that model on a image that's passed into that, they'll get by standard default what that label is. It's like, hey, I think it's a cow or I think it's a camel. But underlying that, you're saying there's more to what is actually happening there.
Yeah, exactly. So for the cow camel example, we might be very certain in one estimate, or we might not be certain in one estimate. And often the cutoff for a binary classification is 50% probability. So a camel so an image that shows a camel with, let's say, 49% probability will be classified as a cow. And that's not very good odds. And that brings into question whether we should trust those forecasts. And essentially what conformal prediction allows us to do is the model is able to specify 4 guesses for any binary classification. So the first guess is that it's a camel. Mm-hmm. The second guess is that it's a cow. The third guess is that it's both. And the fourth guess is that it's neither. And this isn't like very intuitive because it can only be one thing, probably. I mean, there might be a cow camel hybrid somewhere. But yeah, so it allows us for more power and a more explainability into what exactly our image is showing. And if it's not confident enough in the forecast, it will just say, did not compute, error, that type of thing.
So it gives you visibility on the predictive power of a particular algorithm that says, hey, I am giving you this report of what I think this is, and I'm allowing you to change thresholds to provide that answer on a binary classifier, but it'll give you its uncertainty effectively.
Exactly. Yep.
So some of the uses of something like this, if we're not talking about cows, camels, cow-camel hybrids, or things that don't look like animals, if we're talking about something like detecting fraudulent activity as a classifier on financial transactions, for instance, how would we leverage an implementation like this to let the business know that the decisions that are coming out of this model we can either trust or would need some sort of human intervention?
Right. Well, I can certainly speak to that a little bit, but I'll pass it back to you. And I'm curious what the state of the art industry solution is for binary classification like that, where there's very high risk involved, like a very important forecast.
It is using pretty much what your blog post covers and what we've been talking about. From what I've seen, people that have a lot of skin in the game, and it's really very serious that they don't get it right. They're evaluating those uncertainty limits and not relying on the actual label that's coming out of a model, but looking at the probabilities. And then if they really need to make sure that there's true certainty in this prediction, they'll actually determine what that uncertainty is and do a tiered approach. So if we go back to, instead of talking about financial stuff, which can get pretty complicated, but if we're going back to cow camel, and let's say that it's fine if we're a little bit wrong with cows, and we have a video feed taking pictures of our ranch in North Dakota, and we're a cattle ranch, and we're taking pictures of every animal that comes by that camera. If it predicts kind of low that something's a cow, no big deal. We'll just say, hey, it's a cow, because we know that most things are cows on our ranch. But if we're trying to detect rogue camels invading our pasture land, and we really wanted to see if there's just the slimmest chance that there could be a camel there, we might drop that confidence interval for that classification and say, hey, if I detect anything more than 20% probability that I just saw a camel, I want a message to be sent to my phone that I need to get in my truck and drive out there and see, why is there a camel in my field?
Yeah. Rogue camels are a big issue these days.
Yeah, totally.
But yeah, so that's one approach, is to do sort of a manual tuning of probabilities. Mm-hmm. So for something like fraud detection, you might want to be 95% certain that it's fraud, or if you're a very conservative company, 5% certain that it's fraud. But what conformal prediction does is it essentially does this for you, and it combines the probabilities of both forecasts, and it uses those to determine which label it predicts with more interpretability. So with this method that you're discussing, if you go into probability tuning, that can be pretty manually intensive. Yes. There are definitely solid ways to do it, but it's a lot of hands-on work. And this is a nice out-of-the-box solution that works with any model.
So we can actually use this approach and dynamically set an overall alpha for our particular use case without having to go in and say, well, I need to make sure that I'm getting a false positive rate that conforms to detecting camels whenever I see them, and tune my true positive rate. Instead of having to do all that, you can just say, I want my alpha to be 99% or 80%. And then this algorithm will give you a report on that.
Yeah, exactly. And I started to get into the math of it, and it's pretty intense. Feel free to do that as well. I can pull up the paper in 2 seconds, but yeah, it was developed at Carnegie Mellon in 2017 by a guy named Jing Li. And he was a doctoral student, I think, or a grad student. And this was a really impactful paper in that it provided the first universal coverage for any misspecified model. And then he also figured out how to apply it to things beyond probabilistic models. So thinking logistic regression. It can also be applied to continuous variables. Mm-hmm. And this is where the math gets absolutely insane. But what you essentially do is you resample many times until you find out where your threshold is for the 95% confidence interval or prediction interval.
Mhm.
And then from there, you set that accordingly. But it's a mess. But hopefully this will get adopted more in the future. We'll see. But it does tend to produce wider confidence intervals because it guarantees coverage.
So it uses Bayesian methodology to do that sampling and saying, based on what I see in my data, here's what I'm estimating these error estimates are.
Yeah, basically.
That's pretty cool. So if we're going to apply this to other things, referencing continuous features, a lot of people, when they're working on time series forecasting, they have a very distinct need to report out their error estimates to say, here's my confidence that my forecast at this particular time horizon is correct. So can you apply this to those applications as well, instead of having to do exhaustive recursive backtesting?
Yeah, I don't see why not. What are you?
I mean, I think it's definitely worth looking into, and I'm definitely going to do some research on this because it is germane to stuff that I'm working on right now at work. But I know that most of the ways that you calculate this error estimate for temporal data, you have to do a pretty aggressive backtesting regime, which involves stepping through the data set from beginning of time, get your required minimum sample size from start of your time series to a particular horizon point. So if we have 5 years of data, we might say, I need at least 6 months of training data, and then I'm going to predict out the next 30 days. I'm going to calculate my errors there. But to determine your error representation, you're subsampling within that window and saying, hey, I'm going to modify this data a little bit, and I'm going to forecast out what my projected predictions would be if data was slightly different for the next couple of iterations after the training period stops. And all of those projections in the future, you average those up and say, that's effectively what my prediction trend is for that time window. But your error estimate is the range of predictions. So if your model is really bad, your errors are going to be really big, even on a short time horizon.
Yeah, exactly. Yeah, it's like a moving window with residuals. And just as you were speaking, I did find a couple methods for conformal prediction for time series. So that could be a very logical application, because often with time series, we care about interpretability. Maybe it's just me, but I haven't seen many production models leverage time series data. They tend to be more recommendation, classification, that type of thing. And time series forecasts tend to be more interpreted. So like KPI forecasts for planning spend, or how much should we try to acquire new users this quarter, that type of thing, and for setting goals. So if we know we have a valid 95th percentile prediction interval, that can be very useful. And I agree the time series would be a logical next step.
Yeah, because you can get burned in doing a lot of these models if you're just using a single metric that is based on what is the objective error that you're looking at between predicted and actuals. A lot of the times we're dealing with continuous data. We're using root mean squared error or MAE or SSE, whatever our single metric is, that doesn't take into account how variable that is and how much error exists in that particular model. And if we instead use that to do tuning and say, well, yeah, the prediction accuracy is important, but we also want to know how stable this is and how much confidence we can have in the quality of these predictions.
Yeah, that's a really good point, because stability tends to involve, I'm sure you could encode a lot of these decisions into code, but often instability is where people come in.
Yep.
But as I'm saying that, actually, maybe not. Maybe there's a bunch of cool ways that you could encode instability into a forecast itself and then change the forecast accordingly. So never mind.
You can do that. And I have done that before, where you're doing simulations and you're saying, well, we have our historic data and we have a model that's been trained on that, but we want to see what happens if we modify our series and do theoretical next phases. So you'd say, all right, let's say we have 6 months of training data and we want to predict the next 2 weeks, but we want to know where could that prediction actually go. So if your data set is surrounded, let's say in the range of 800 to 1200 as a float, and we're just predicting this range of data, and we say, all right, 2 weeks out, I want to see what's going to happen if for the next 4 or 5 days after my training data is complete, my real world data, what happens if our sales go up 50% in 5 days? What happens if it goes down 50% in 5 days? And then you start searching these different combinations of things that could happen, and you forecast that out and see what happens. And that simulation, a lot of companies use that for decisions, and they're not doing 2 weeks of prediction. They might be doing the next 6 months of business performance, or you could be modeling out your number of users. Well, what happens if our user base just goes to some other platform or uses some other service abruptly over the next month? What is that going to do to our business or our total user base or our sales or whatever? The complication that comes in there is it sucks to write that code. It's complex. It takes forever to run. It's expensive. And a lot of times it's fragile in the sense that it's really hard to maintain that code. Like, what are you going to test?
Yeah, no, I can certainly imagine. Yeah, that's something that I've been working on recently. Sorry, go ahead.
No, I was saying this approach solves that for you, basically, with just a single parameter that you're changing.
Yeah, no, it is very nice to have.
Hi, this is Charles Max Wood from Top End Devs, and lately I've been coaching some people on starting some podcasts and in some cases just taking their career to the next level. Whether you're beginner going to intermediate going to advanced, whether you're trying to get noticed in the community or go freelance, I've been helping these folks figure out how to get in front of people, how to build relationships, and how to build their careers and max out and just go to the next level. So if you're interested in talking to me and having me help you go to the next level, go to topenddevs.com/coaching. I will give you a 1-hour free session where we can figure out what you're trying to do, where you're trying to go, and figure out what the next steps are. And then from there, we can figure out how to get you to the place you want to go. So once again, that's topenddevs.com/coaching.
And I didn't get too deep into the weeds of things like built-in, for instance, Facebook profit for time series is like a classic out-of-the-box algorithm that performs solid. I didn't get into the weeds of how those prediction intervals differ, but I think they use a pretty vanilla approach. So I'm curious if conformal prediction becomes more widespread and more generally accepted by industry. So we'll see.
I mean, it's definitely something I'm going to start taking a look at over the next week.
Sweet.
I really want to see what options are out there and how challenging it would be to implement this as a general scoring methodology for time series in particular. Because, you brought up Facebook profit, and it is sort of I guess you could call it vanilla. It's sort of the standard way of doing error estimations to determine how good of a prediction this is going to be through back testing and setting these sliding windows and saying, hey, if I modify this data just a little bit, what is it going to do? How much is the error going to increase? And then you just have to do that over many, many, many sliding windows and recursing over that over and over and over again. And then it's an average of those averages that give you your metric reports for health and variability. So you were saying you were working on something else recently.
That sounds great. And I'm assuming your work is going to be open source.
Oh, I don't know. This would just be
a bit of a lag.
This would be satisfying my own curiosity, and then we'll see where it goes from there.
Got you. Cool. Yeah, I just wanted to also bring up another interesting approach to this. So, and finance is one of the easier ways for me to think about this because I worked in the industry for a little bit, and I think it's just a very number-hungry application. Mm-hmm. But another approach to this would be forecasting quantiles. So instead of forecasting the mean, which is what most forecasting models do, you could forecast the top 20 percentile or the bottom 20 percentile. And then you can use those to better inform your decisions as to whether the forecast is good enough, bad enough, etc. And that's another approach to it. You don't have, I mean, you would need to put prediction intervals around that quantile.
Yep.
But then if you know that being wrong in one direction is a lot worse than being wrong in another direction, if you forecast a little bit in one direction, you might be actually saving yourself a ton of money.
So you're saying that by plotting out, even if you just start with just IQR and just say, hey, I want to see 25th, 75th percentile and what that variance is in my forecast, you could see that it's what its distribution type is. You say, hey, our error estimates are not normally distributed. They're exceptionally right-tailed or left-tailed. And that can help inform a decision maker who's consuming that to say, maybe we should hedge our bets here and not do things in this direction.
Yeah, I mean, that wasn't even what I was saying, but that's a great idea too. What I was saying is that regardless of the assumed distribution of our data, we just forecast a quantile, and then we use that to make decisions. But I like your idea a lot as well, because if we know that it exhibits some sort of distribution, we can know that there's a lot of density in a certain area. So if we forecast where that density begins, we have a lot safer forecast than forecasting the median, because just look at any distribution chart that isn't a normal distribution and plot the mean, median, and mode.
Yep.
You'll see that they're all over the place.
Oh yeah.
So you're 100% right. Knowing the distribution itself would be very valuable.
And currently there's not really a lot of easy, high level, out of the box APIs for that. I don't know if you've ever had to do something like detect my distribution on a continuous data set. Doing that the brute force way, where you're just saying, hey, I'm doing effectively a comparison of these different distributions and saying, how well do these PMDs and PDFs actually match up to a standard normal or any of the, I can't remember how many are in stats models in Python, but I think there's over 50 that have been defined. So there's standard functions that describe these distributions. And to do that comparison, it's brute force. It's saying which one matches the best after scaling the data and getting it into effectively like a histogram representation.
Yeah.
But with this approach,
there are tests
to do that.
Yeah. That is true. Yeah. And I was just saying that there are tests for equality of distributions, but they often use key statistics like a median.
Yep.
to determine whether something is the same. And that's not good enough. One of my coworkers actually, he studied at UC Berkeley, and one of his profs came up with that. I don't know if he came up with, I've seen it in other places too, but the concept of a B-score, which is the overlap between two distributions.
Mm-hmm.
And then you can use that as sort of a p-value-esque type thing. So yeah, whatever percent of the distribution overlaps is how similar they are.
Yep. An approach like that is in stats models. I can't remember the actual name of the API for that, but it involves, if you're going to implement that as an end user, if you're a data scientist who's like, hey, I need to get estimates of how successful this prediction is in estimating how much it can be trusted effectively and where it could go wrong for predicting like the financial data over time. And a lot of people look at that forecast, even if they're plotting their error bars through back testing and estimation, they look at that and they're like, oh, it kind of looks normally distributed. But with using this SI approach that you're talking about, we can look at that actual distribution of errors that are coming out and saying, well, or plotting the quantiles and forecasting those, we could say, well, it's actually it's pretty close to this distribution, but writing all that code is pretty painful, regardless of what test you're using.
Yeah.
And to doing normalcy checks, there's a bunch of different ways to do that. There's over a dozen different things in most of those open source libraries that allow you to do different tests for different families of distributions. Some are only valid for comparison for if you have this type of distribution. It's just a lot of research and a lot of reading, a lot of testing. It's painful. You could be looking at a validation part of your code base for a particular implementation where this validation checking and reporting on your confidence of how much this solution can be trusted could be 10 times bigger than the actual code that's building the prediction.
Yeah, that's no fun.
So this is cool. This is definitely cool. Like today I learned, and tomorrow I'm going to learn more about this. So we'll definitely link this in the podcast and make sure that people can get this tutorial, look at what you've written and the research that you did, check out the original research paper. If people want to see just how crazy this math does get, it does get crazy. And then start really thinking about how important this is. And it's a common theme that I've seen in industry where people are all about just getting that model aspect of ML working, or some people are focusing on, hey, I just need to solve the problem. But a lot of the underlying things that show up only after something's in production and people start asking questions about, hey, I saw the predictions that came out of this model over the last week. I don't buy it. I don't trust it. Prove to me that it's good. And a lot of the ways that you handle that is through statistical evaluation. So I think this is great, seeing that people are still thinking about this and thinking about it even more about, hey, there's a prediction isn't a certainty. It's not, hey, the model predicted that it's a camel, so it's got to be a camel. There's a probability associated with that, and being able to consume that probability and present it in a way that the data scientist building the model can understand how good of a prediction that is, as well as the end user having an indication of how certain we are that this is performing correctly, is incredibly invaluable.
Yeah, I could not agree more. And corny call to action, but if you guys want us to discuss future topics, we have more guests coming. But if you guys want any topics covered, we're happy to do that. I'm working on my blog for another 6 months-ish. So if you guys want anything covered through that, like white papers, I will at least consider it. So just let us know.
And that's just for the first 52 posts. When people start asking
I think we're going to be done at 52.
I think it'll hit 520. Do a 10-year. Do a blog a week for 10 years. Think of how much you're going to learn.
That's an option. I'll consider.
So what are some of the other stuff that you've been writing about recently?
So I've been actually really busy. So I've been putting out pretty crappy posts. They're things of personal interest, but they're not super technical, and technical posts take up a lot of time because you have to actually learn them. But I've been really interested in simulations for physics-based bodies, essentially. So in other words, how to develop wind turbines and even things like marine energy turbines through simulations. Because prototyping those is really expensive. So if you can develop simulations, that's a cool area that I've been exploring.
And that's a realm of data science that a lot of people that are doing what's most talked about in predictive modeling of like supervised learning and unsupervised learning and deep learning, people are like, oh yeah, that's ML. It's like, well, there's this whole other side. There's many other sides of ML work and data science work that I'm looking at the blog post right now about digital twins. And that realm of ML is very different than traditional ML. And a lot of people run this stuff not on their laptops and sometimes not even in the cloud. It's usually high performance computing clusters that are doing these simulations and running through basically what if scenarios.
Exactly. Yeah. And a lot of this is like written in Fortran, built at national labs because it's not profitable yet. So they just throw compute and low level programming at it. And they get some okay results, but I think there's a lot that can be learned in that area.
Hey, folks, if you love this podcast and would like to support the show, or if you wish you could listen without the sponsorship messages, then you're in luck. We're setting up new premium podcast feeds where you can get all of the episodes released after Christmas 2020 without the ads. Signing up will help us pay for editing and production, and you can go sign up at devchat.tv/premium.
But what about you? What are you working on?
Oh, recently, we're just working on more ML flow stuff and features that the team is looking to bring into recent versions. We just had a release this past week of the next version of ML Flow. The team's adding some good quality of life features to it right now. in the next quarter, there's going to be some interesting developments happening with that tool, most especially surrounding a lot of what we've been talking about today, at least at a higher level, model explainability. And how do you get that so that it's easier to actually do that? Everything that we talked about simplifies that to a certain degree when we're talking about, okay, here's a different way to determine your confidence intervals of a prediction without having to do it the brute force way, because the brute force way is painful. It takes a lot of time and a lot of code. But model explainability and evaluation of prediction success is something that when you're outside of the tuning phase, a lot of people see it as an afterthought, or it's only ever built around a model when you need it. And usually when you need it is in a panic mode. And that panic mode, with our analogy that we were using earlier about cows and camels, would be, what if somebody releases 100 camels into the pasture and then the model's not predicting that correctly? It's just seeing cows. The farmer's going to, or the rancher's going to say, hey, this prediction sucks. Like, what is going on? And if you have to explain how it was making those decisions at the 11th hour, and you're kind of in a defensive mode and panicking and not implementing everything that you probably should to effectively explain that prediction. So what we're looking at is, how do we make that simpler? How do we make it so that if you want to explain a particular model, just give us your data and the model artifact, and we'll run SHAP for you. And we'll get all of the metric evaluation reports, the visualizations. They'll all be created for you. It's just a one-line API call.
That's huge. And I know that model explainability is becoming one of the hottest topics out there. So I'm excited to hear that. I know there are a couple other companies in the space, specifically model explainability, but I mean, Databricks is Databricks. So,
I mean, it's incredibly important. And anybody, myself and you, like, we've worked in industry as data scientists. We know what it's like to have to maintain something and have to talk to internal customers about our solutions and have to do that explaining. And we can't break it down in terms that we would explain it to one another. You can't be like, whoa, I'm looking at the confusion matrix, and here's our area under our ROC plot. And, if we just tweak this to reduce the false positive rate, you can't talk about that with the business. That person who is consuming that model or is in charge of that project from a business standpoint, they're going to be like, what are you talking about? Like, I can conceptually understand what this is about these percentages and stuff, but if you start talking geek to them, they're just going to tune out. So having the ability to graphically show something that distills down what is actually going on in a consumable way is incredibly important. And having it on demand, where it's very simple to generate that, is absolutely crucial.
Yeah, that is huge. Wow, that's awesome.
And it's fun building that stuff and seeing other people that are on the team building it. It's just amazing.
Yeah, it's nice to have a very tangible outcome of your work.
Yep. And helping other people solve problems is great.
True. All
right. So we got to think about some stuff for next time. But if anybody wants to hear another in-depth geek discussion, just like Michael said, let us know, and we'll cover some interesting topics. If not, we're going to pick another one of the things that you've written about in the last, 8 months that you've been doing this?
6, like 7.
Yeah. So we'll do a random selection of something else that's incredibly interesting that not enough people are talking about, and we'll dig into it in this way, because stuff is very fascinating and incredibly useful.
Yeah, good with me.
All right. So is there anything else you'd like to mention?
Nope. I think I'm good. How about you?
No, I'm good. This is it's good fun chat, and it was great geeking out and really talking about something that is up and coming, that is incredibly useful, and is probably going to be another great tool in our toolkits as ML practitioners.
Yeah, I hope so.
All right. So until next time, this was Ben.
And this is Michael.
And we'll see you next time. Bye.
All right. Thank you.
Bandwidth for this segment is provided by CacheFly, the world's fastest CDN. Deliver your content fast with CacheFly. Visit CACHEFLY.com to learn more.